Collection of Thermal Energy Through Roads and Water by Robbie Vachon. The purpose of this experiment is to test the feasibility of collecting thermal energy from the sun via tubes implanted in roads. The question I posed was this: can a change in the surface temperature of a road due to the thermal energy produced by the sun cause a temperature change in water stored in tubes inside the road, and does time have any effect on this? This procedure has been suggested by a civil engineering firm called OOMS, based out of the Netherlands. My background research, which consisted of research of the company's public documents regarding road energy systems, suggested that because asphalt becomes hot under sunlight, the road beneath the surface becomes heated as well, enough to heat water constantly pumped in a closed circuit through the road. Also, I found that roads can become very hot in some months, up to 20 degrees hotter than the air temperature. So, in correlation with what I found through my background research, I hypothesized that an increase in surface temperature of the road would directly relate to and cause heating in the water cycling through it. Another facet of my hypothesis was that the more time would cause an increase in the temperature of the water with a constant surface temperature. To test my hypothesis, I constructed a model road. I researched the construction of roads and mimicked the exact compositions. The first layer is a layer of sand, which is the aggregate, followed by a layer of gravel, then a mixed layer of gravel and sand, and finally a layer of asphalt. In addition to normal road construction, I also included a scale representation of the piping system described in use in road energy systems. I connected the ends of the pipes to a water pump to allow the cycling of water through and under the asphalt layer of the road model. I used a heat lamp suspended from a tripod to simulate the heat generated by the sun. I recorded the surface temperature of the asphalt as well as the temperature of the water before each test. My first series of tests were each 20 minutes long, with the heat lamp suspended 15 inches above the asphalt surface. For each of these tests, the beginning surface temperature was 60 degrees Fahrenheit, and the temperature of the water was 55 degrees Fahrenheit. I did 3 tests in 20-minute time periods. I did a variation of this test with the lamp suspended at the same height, but in 10-minute increments rather than 20. My second series of tests were conducted with the lamp 8 inches above the asphalt surface. They were conducted in 10 and 20 minutes as well. There were 3 tests for each increment of time, i.e. 3 tests at 10 minutes, 3 tests at 20 minutes. To measure the surface temperature, a layer of foil was used to insulate the thermometer, which was placed flat on the asphalt from the air temperature. To measure the water temperature, the pipes were removed from the pump and the thermometer was inserted into the tube. Air pressure was applied to force the water around the thermometer. My data, as displayed by these graphs, shows a direct correlation between the temperature of the surface of the asphalt and the temperature of the water. My data also shows that a higher temperature on the surface means a higher water temperature, as my tests with the surface temp at approximately 105 degrees Fahrenheit yielded a 3-degree increase in water temperature over the results of my tests with the asphalt around 72 degrees Fahrenheit. My data also shows that the time had almost no effect on the temperature of the water, with no difference in the results of 10 and 20 minutes tests at the same temperature. After testing using the model, I reached the conclusion that my original hypothesis was correct. The original assumption that the surface temperature would directly affect the temperature of the water in the pipes was correct. An increase in surface temperature corresponded to an increase in water temperature. I also concluded from my data that water temperature did in fact increase from its starting temperature, proving that thermal energy does travel through roads into pipes embedded in them. The secondary facet of my hypothesis, that a greater period of time would allow the temperature of the water to be closer to that of the surface, proved to be completely false. The data I collected also led me to reach the conclusion that the amount of time the model road was subjected to a constant temperature had no effect on the temperature of the water, as they reached the same temperature in both 10 and 20 minute time tests.